Hello viewers, welcome back to another section of my tutorial. In this video I'm going to take you through Norton's theorem. So Norton's theorem is similar to Thevenin's theorem, and they all help to simplify bigger networks to get current in particular resistors easily. Now, Norton's theorem simply states that any linear circuit connected between two terminals. So I showed you, if you have a complex circuit and they are all joined to a voltage source. So if you have such a circuit and you want to find a current through one resistor, Norton's theorem is saying that a linear circuit here can be replaced by a Norton's current. So see, you have a Norton current, then you have, so the Norton's current is represented by IN. So he said it will be replaced by a Norton current in parallel with a Norton resistance Rn. So let's see. This brings us to the Norton's equivalent circuit. So Norton's equivalent circuit. So in this circuit, Norton is saying that any linear circuit connected between two terminals can be replaced by a current source called the Norton current and Norton's resistance Rn, and they are in parallel. So these two terminals are for the linear circuit which has been replaced. And within this circuit, you are going to place the resistor you want to find the current through. That is our resistor. And the current here is what? Here is our current source IN. And IN upon reaching here will split into I. And that I will come and pass here. Some 2 will split here. So this is Norton's equivalent circuit. Now let's say the circuit and the theorem once again. The theorem is saying that any linear circuit connected between two terminals can be replaced by a Norton's current in parallel with a Norton's resistance. And the two terminals here has a resistor here which we are finding current through that resistor. Let me take a question for you to understand how this works. So I have a problem here. So let me write the question I have. So using Norton's theorem, determine the current in the 3 ohm resistor. So see, I'm using this circuit. So now this circuit I have here, there is a 35 volts here, there is 42 volts here, this place is 12 ohm, and this place is 3 ohm, this place is 6 ohm. Once I have this, now let's see what the theorem says and how we can apply. So this theorem looks similar to the Thevenin's theorem, and you know Thevenin's theorem is saying that we are using a Thevenin's voltage and Thevenin's resistance. But in Norton's theorem, we are using Norton's current and Norton's resistance. So let's see. The first step, we are going to remove the resistor from the circuit and make 2 terminals. So now this is the resistor we want to find. So remove this resistor. So you have the 42 the 12, then I have the 6, the 12 here, and the 42 volts. And this here, I'll remove my resistor here, then this is the 35. So I have removed the resistor, and let's see, Norton is saying that replace the resistor here with a short circuit current. And you know, short circuit current, we close this part and we design a direction for our current, because the current will have a direction. So let's see, the current is moving this way. The current is moving this way. So the current is called IN, right? That is Norton's current. So the current is moving this way. So we have assigned the direction for the current. Now the next thing to do is to find this value. To find this value, let's see. This voltage source here is producing a current. Let's say I. The current will pass through here, and upon reaching here, what will happen? By applying Kirchhoff's current law, you see that the current that will be passing through this side will be what? This one will arrive here, this one is leaving. So to find the current passing through 6 ohm resistor is going to be I minus IN, because this operation was split into IN and IN. This I was split into IN, and the rest will pass through 6 ohm. So the rest is I minus IN. Once I have this, I can take a loop, and the loop will help me get the value for I. So now, let's see the loop I'm going to take. Let me take this loop. So in this loop, I'm going to have my total voltage was, let me take it this way, 42 is equal to my voltage drops. Here is what, 12 multiplying I, plus here is what, 6 multiplying I minus IN. Is that not it? So once you have this, I'm going to have 42 is equal to 12I plus 6I minus 6IN. So at this point, I'm going to get 42 to be equal to 18I minus 6IN. And this is the first equation I have down. At this point, I'm going to take another loop and see how I'm going to get the value for IN. So now let me take this loop. When I take this loop here, this is what I'm going to get. So let me take this direction, right? So when I take this direction, I'm going to have 35, because it's in the positive way, that direction. 35 to be equal to, here there is nothing here, there is no resistor, so there will be no voltage drop here, so it's 0, but there will be a voltage drop here, and that will be 6 open bracket I minus 6 IN, and this is equal to 35 is equal to 6I minus, sorry, here there is no 6 here, so I minus IN. So is equal to 6I minus IN. So 35 will be 6I minus 6IN, and that is equation 2. If I solve this equation, let's see, I have 6IN, I have 6IN, right? When I subtract this from this equation, I'm going to get what? 42 minus 35 is 7. So 7 will be equal to, when I subtract this and this will go away, and I'll get 18 minus 6, and that will give me 12I, right? So when I get 12I, I'm going to get my I to be equal to 7 over 12. And when I have I to be 7 over 12, I can find my IN by putting it into any of the equation. 42 is equal to 18, 7 on 12 minus 6 in. So 2 will go here. Now let's say 3 will go here, 4, 3 will go here, 6, right? 2 will go here, 2, 2 will go here, 3. And I'm going to get 42 to be equal to 3721 on 2 minus 6 in. So this is going to give me 10.5. So 6n will go this side, then 42 will come. So 6 in will be equal to, so 21 over 2 is 10.5 minus 42. So now we solve it to get our in. So if I have 10.5 minus 42, I'll get negative 31.5. So 6 in will be equal to negative 31.5. So this is 10.5 minus the 42. So this is what I'm getting. Then I divide through by our 6 to get my in. So my in will be simply negative 21 on 4. Negative 21 on 4 amperes. And normally when you are doing applied electricity, take note, don't be leaving your answer into decimals. It's preferable to leave it into the fractional notation to avoid run-off errors. Once I have my in, the next step is saying that you are to deactivate all the sources as we did in the Thevenin's theorem. After finding your in, the rest is the same as Thevenin's theorem. So you are going to deactivate the sources, then after you replace the replace the Norton's current with Norton's voltage. So let's see. I'm going to deactivate the sources. Deactivating the sources, our voltage source will become a short circuit, no 42, and this side I'll have 12 ohm. I'll have 6 ohm. Then this side will be Rn, that is Norton's resistance. This place will be short circuited. So my Rn obviously will be equal to 12 and 6 in parallel. So 12 times 6 over 12 plus 6, 72 over 18 is equal to 4 ohm. So now let's come back to our Thevenin's resistance, Thevenin's equivalent circuit. And Thevenin's equivalent circuit is saying that we are going to have our In, then we are going to have our Rn. So let's see what we are going to do. So let's see. So I'm going to have my Rn to be equal to my In. The total current will be in parallel to the Rn, then in parallel to the resistor. So the Rn is negative 21 on 4. The resistor Rn is 4 ohm and the resistor is 3 ohm. So this is I. So you are going to use current division rule to find a current through the 3 ohm. And you know that to find a current through the 3 ohm is simply going to be equal to the 4 ohm, that is our Rn, over Rn plus our R times the total In. That is the current division rule. So our I will simply be equal to our Rn, which is what? 4 plus 3 times negative 21 on 4. This is equal to 4 on 7 times negative 21 on 4. This will cancel this, and my current will be equal to negative 3 amperes. Thank you for joining me in this video. Hope seeing you in the subsequent videos.